Hello, everybody.
Hello.
Welcome to our stream. We're just going to wait a second for everybody to join, everybody to refresh the page. I hope you're logged in so you can ask us questions. Today's going to be a very thought-provoking subject on dark matter. How
Feel
have you
free
all
to
been?
say hi in the comments.
I'll start with some introductions. My name is 𝐀𝐜𝐭𝐢𝐯𝐢𝐭𝐢𝐞𝐬. I'm the theater manager at Fiske Planetarium. And while Fiske is not open to the public, of course, because of the current looming COVID crisis, we are trying to host things online. And so that's what we're doing today. And Dome to Home, we'll be talking about dark matter. And I'll let Amanda introduce herself.
Yeah, as he said, my name's Amanda, and if you've seen me on any of the other videos, you know that I'm also super excited that we're doing this. I think it's a great way to learn some really special astronomy and get your Fiske fix if you're missing it. I'm a CU Boulder student and a navigator, and I also can't wait to get back in the dome, but I'm really enjoying what we're doing here. So hopefully you guys like these lessons.
Absolutely. Well, let's get started. So with that, let's take a look at what we're going to be talking about today. Today is about dark matter. And dark matter is a very interesting subject. In fact, it makes up a lot of the universe. We can see that when we look outside at night at just the stars, there's a lot of stuff there that we're not seeing. And we can see it in things like this, like gravitational lensing. It makes up something like 25% of the universe. So we really should care about it. And what's strange is that everything you can see, everything you can interact with, is part of the universe, but dark matter doesn't seem to really interact with you the same way everything else does. So that's what we're asking today is, why does dark matter matter, and when does dark matter matter? So we're going to start by asking, to break up that term, those words, what is dark and what is matter? Because that's not the best way to understand it. Astronomers tend to explain things in very, very simple terms, like sunspots are spots on the sun. So dark matter, what is that? Well, let's first break down the word matter, because that matters. All of us hopefully appreciate that stars are matter, right? When you look up at the night sky, you can see the stars. That hopefully you know that you're made of matter. You do matter. That things like matter can have different states. It can be in a liquid state. It can be in a gaseous state. I'm breathing in air. It can be solid. Matter can be anything that you can interact with. Everything from you to the Earth, the moon. People can land on the moon. Other galaxies. Stuff just like stuff you can eat. It's all matter. And the main thing about matter is that it interacts with the universe through gravity. That it has a sort of weight to it that pulls stuff together. In fact, if you were to get enough of it together, you could start to form things like planets and the moon. In fact, we're reminded that the Farron Field here on the CU campus, all the trees, the mountains, they're all part of this Earth. They're all made up of matter. So what we're going to do here is we're going to leave the Earth, and we're going to try to appreciate the size that of things uh, that matter can take, right? Can form so much gravity in one place. So, for instance, the Earth is so large it can control the moon with its gravity. The moon is smaller, so it only controls the tides on Earth and a little bit of the weather. The Earth, the moon together are controlled by the sun through its gravity. It's so much matter in one place, its gravity helps to pull the moon into orbit around the sun. And of course, the Earth, a little bit less gravity, only pulls the moon into orbit around it. All the planets in the solar system are bound to the sun through the sun's enormous gravity. There's so much matter in one place. Of course, the sun does much more than just keep the Earth in orbit, it provides us with life, sunlight. But let's actually keep expanding our scale. The same way that the Earth controls the moon and the sun controls the Earth, all the stars in the galaxy help to control each other. So we're going to leave our solar system behind. Everybody say bye, solar system.
Bye.
We're going to travel where no one's ever gone before, out to the edge of our galaxy.
And not even just where no person's ever traveled, we also haven't even sent spacecraft out there. So this is an extra special journey out to our own galaxy.
As we're flying past these different stars, these are all different sources of matter in our galaxy. Each of them together weighs something. They each have their own solar systems, and in between them there's an enormous amount of gas and dust. These stars, that gas and that dust that we can barely even detect, all make up our Milky Way galaxy. We just left a single arm of our galaxy, or a spur. The Milky Way galaxy has something like 100 billion stars in it, 200 billion stars. And if we were to weigh them all and try to account for all of this matter, we would be able to try to count it in a form of stars. Maybe we could say there's something like 1 trillion suns worth of stars, worth of matter. 1 trillion suns worth of matter in our galaxy. We can try to count it and try to weigh it, try to account for all the gravity in our whole galaxy. So this is matter. But to understand the other part of dark matter, we need to understand what they mean by dark. So astronomers think about the term dark. And they describe dark as saying, it's something that we can't see. In fact, this picture of our, or not a picture, but this is a model of our galaxy that we think is what our Milky Way galaxy probably looks like. In this model of our galaxy, there should be an enormous amount of dark matter that we can't see because it doesn't interact with light. Even though there's 200 billion stars beaming with light, we don't see the dark matter within this galaxy. In fact, we think it's all around our galaxy in an enormous what we call halo. And so the stuff that we can actually see that actually interacts with light, that matter, the visible matter, just makes up a small portion of this enormous cluster. Now they're showing it here as a big sphere, but it's probably like very tenderly. There's probably lots of streams of dark matter. And so that dark refers to the fact that it doesn't interact with light. You can't shine a flashlight at it. You can't shine the stars at it and see it. The light just goes straight through it. And it doesn't really care about light. However, there's also another reason, is because we know so little about dark matter. We know so little about dark matter that it's purely a term to stand in for the fact that we see it working, but we don't know really what's causing what we see. We see something happening in the universe. We see something's happening, but we don't really know what is causing it. So we call it dark because it's mysterious. It has to be some sort of matter, we think, but we don't really know how to explain it.
But we can look at lots of clues that help us think and figure it out a little bit more and come up with some theories. Right, Nick?
Absolutely. In fact, one of my favorite demonstrations of this is this picture. So what do we see in this picture? These are some telescopes atop a mountain in Hawaii, Mauna Kea. But if you look off in the distance, you can see there's a shadow from this mountain. It's got a sharp pointed shadow. This shadow tells us that we're standing on a mountain, and it's got a big sharp point on it, right? But I don't see the mountain. I see the hills in front of us, but where is the mountain? Well, we can see that it exists because of its shadow. We can't see the mountain, but we know it's there because of its shadow. I think you might have another for us, Amanda.
Yeah, we've also got this picture, another shadow, and we can see this is the shadow on the Earth. So we're looking down at the Earth and we see this shadow, and it's got to come from somewhere. So we can use our powers of observation and infer that that's probably the moon, because the moon goes around the Earth, and if the sun shines just right, the moon will cast a shadow on the Earth. So we don't see the moon in this picture, but we know that it's close because of the shadow that we see on the Earth. So lots of clues to look for.
Yeah, so even though we can't see the moon, we know it has to be there because we can see its effect on the Earth. So to better understand this, we're actually going to travel back to our solar system through our galaxy and try to look at some normal matter. Because maybe understanding how normal matter works, we can understand how dark matter works. So here we go, diving back through our sea of stars. Which one is our sun? We're ramming through clouds of dark matter on our way back to the sun. We just can't see them.
And it's always a good idea, if you don't know about something, to start with what you do know and work backwards from there. So great idea going back to the Earth, Nick.
Yeah, just to look at our solar system, I really like that, Amanda. To start with what we do know that the planets in our solar system go around the sun, right?
Mm-hmm.
And we know that they go around the sun in these big ovals. They've been doing so for millions, billions of years. So let's actually try to look at how they move around our sun, because that way we can appreciate how the gravity of the sun affects the planets. There's a hidden message here that we know that dark matter doesn't interact with light, but it does through gravity. That's the first big point. Dark matter works through gravity. So if we can understand the gravity working on things that we can see, maybe we can understand gravity working on things we can't see. So what we're going to do is we're going to speed up time and look at our planets going around the sun. And now they're moving backward. So we're going to flip around. There we go. They orbit in this counterclockwise direction. You can use your right hand to see how they move around the sun. And we can see them moving. Which one's moving the fastest? And which one's moving the slowest?
Definitely looks like those inner ones are whipping around pretty fast.
Yeah, the Earth is having quite a ball down there. So the ones that are closest to the sun move the fastest. And as they get further from the sun, they go slower and slower and slower. This is how gravity works. The further away you get from the source, the slower it goes. And the sun, being the biggest source around, is causing a lot of gravity. Of course, these other planets, we've made them much larger, so they look really big. Technically, they're very tiny in comparison. So let's see if we could graph. What if we had a graph of showing us the speeds of these planets compared to their distance? So on the far left, we can see Mercury moving the fastest. It's got very high up on the graph. And then Venus is a little bit slower. Earth, Mars, Jupiter, slower still. As we get further from the sun, Saturn, Uranus, Neptune, and Pluto goes even slower. And so we've made this line to represent in the graph how the closer you are to the sun, you're going very fast, and the further you get from the sun, the slower you go. This is what we expect to see with things working through gravity. This is Kepler's motion. Maybe we could try to look at this at the size of our whole galaxy, right? Because we know that our sun moves around the galaxy, so let's try to understand other stars moving around the galaxy. This is where dark matter becomes important. Dark matter starts to matter at very large scales.
So let's roll up on a spinning spiral galaxy, perhaps.
Yeah, so as we leave our galaxy, we'll be reminded of the way that galaxies move over time. We just sped up time for our solar system to many years a second. Here we're seeing millions of years move by in this galaxy every second. And you can see the stars, the gas, the dust all swirling around that galaxy. And they're swirling around the center. So the gravity of all the stars at the center, you'd expect, would be like the sun, that it would help to pull all the other stars into an orbit around them. And all the other gravity of these stars that we're flying past right now would help to pull the stars around. And the ones closest to the center would go the fastest, and the ones furthest from the center would go the slowest. But the strange thing is, when we look at the scale of galaxies, we don't see that. So here we have a picture of a galaxy, and we can spot the center of the galaxy as the center of that graph, as the bottom left-hand side of that graph. And if we use math to calculate the same thing happening with a galaxy as we did with the solar system, we would see the red line. See, at first, there's a lot of matter in middle of the galaxy, and the speed goes up and up and up, and then the speed drops off as we get further and further from that matter, from those stars. The speed drops off like Kepler's motion. That's the red line, the bottom line. It says calculated on it. That's what we think should happen. Because that's what happens in the solar system. That's how gravity works. But strangely, that's not what happens in real life for galaxies. Once we look at almost every galaxy in the whole universe, they all follow the white line, that top line. That the speed of the stars moving around the galaxy increases as they get further away, and then it stays the same. It doesn't fall off. So the way Pluto and Neptune go slower around the sun is not the same way that stars go slower around the edge of the galaxy. And this doesn't make any sense to astronomers who are trying to think, well, gravity should work the same way, no matter if it's working on the size of a solar system or the size of a whole galaxy. We expect that gravity should be the same. So why is it that the speed stays the same? Whether you're toward the center or if you're toward the outside, the outermost one should go slower.
You know, a very smart lady named Vera Rubin had a very similar question.
In fact, it was Vera Rubin who really put a face to the name of dark matter. She helped us to understand just why this happens. She helped us look at numerous numbers of galaxies and she saw that all of these galaxies pretty much did the same thing. It seems like all galaxies have some extra material in them, something around them that helps to pull the stars faster than they should be going. So in this galaxy here, we would expect that the stars on the outside should be moving faster than they should be going because of this dark matter. And so she confirmed by looking at all these different galaxies, they all behave the same way. It wasn't just one or another, they all had this strange quirk about them. Pretty mysterious. Now, what Vera Rubin did is to help us understand that this is common. And in fact, it's not just common with the way that stars move around other galaxies. This is common when you look at large clumps of galaxies. So what we're going to do is we're going to leave the Milky Way behind, and we're going to start looking at a lot of galaxies. Because we're not the only ones out there. Astronomers believe there are trillions of galaxies in the universe. And we're going to look at just a few tens of thousands. Now, on the small scale, our galaxy is actually quite large. The Milky Way galaxy is a medium to large sized galaxy. There are smaller ones who are bound by its gravity and they move around. We saw the large and small clouds of Magellan down there. And now we're looking at tens of thousands of more galaxies. Every dot you see is a different galaxy. So what astronomers use their telescopes to look out between the stars at these distant galaxies. They see that these galaxies are everywhere, and they see that there are tens of thousands of them just within the local region of space. And one thing's for sure, that when they look at these galaxies, they're not quite this big or this bright. We're definitely enlarging them and making them look brighter than they really appear. Astronomers need to use massive telescopes to get a good picture of them. But they see something strange happening to the biggest clumps. So let's look at, say, the left-hand side. We see this big clump coming up. That, I think, is the Virgo supercluster. We call these clusters of galaxies, superclusters of galaxies. And we have a few pictures of what happens around some of these big clusters of galaxies. So Amanda, if you can bring up one of those for us.
Yeah, absolutely.
We saw one in the beginning that made that beautiful smiley face, but here we're seeing there's this big orange dot in the middle, and there's a sort of blue U shape. And this is very strange because what this is, well, it looks like it's just like somehow something stretching around in outer space. It looks like a problem with the camera. But really, this is the fact that everything that has matter has that gravity. And gravity can change the way that light moves. It can warp space-time. So we have a great demonstration here. This one is showing two distant stars. Or sorry, a distant star. This one star very far away. And as its light tries to move through space, it gets bent by the path of the sun. The sun's gravity and its mass warps space-time, this sort of fabric that we all live in. And that means that the beam of light, the solid line that you see, is getting bent by space, and it eventually starts to go on a straight path straight into the telescope. And so if you were to trace that straight path all the way back, it looks like it's coming from a different place. So we can make things appear to be coming from different places than they're actually coming from. And that's what's happening in this picture, is that behind this big orange blob in the center, there is a distant galaxy. And that distant galaxy is being warped around the blob into these two images of it on the side. It's getting duplicated and it's being stretched out because of the mass that's there. And on this massive scale of these enormous galaxy clusters, you can see lots of these blue streaks, lots of elongated galaxies. And when astronomers count up all the mass inside these clusters, they find that there's just not enough mass to make this happen. They can try to count every star, they can try to count every speck of dust and every cloud of gas, and they can't account for all of these streaks. It seems like the amount of mass to warp space-time enough to cause this streaking and the sort of weird effects uh, of warping space-time. This must be caused by some extra matter being there, something that we can't see, right? Trillions of stars can shine on it, and we can't see it. And maybe, just maybe, um, it actually is interacting um, through its gravity in a way that is warping the space-time enough that we can see these strange effects. So we think that dark matter is affecting, is causing this to happen. Now we don't know what it is, right? We don't know if dark matter is it like sheets of material? Is it a particle? Is it some sort of field? We don't really know, but we know that it has to interact with gravity. And that's where astronomers get very confused because we see what's happening in space. We see the stars moving around galaxies really weird. We see that these galaxies are clumping up and they're creating this lensing through the gravity, what we call gravitational lensing, these weird blue streaks of galaxies. So we see these things happening, but we don't know why. And we think it has to be some kind of matter that we can't see, some dark
And we can see it happening on all of these galaxies, and so we're able to map it pretty well, right, Nick?
matter. Yeah, we can try to map it. In fact, when we use gravitational lensing, we can try to map the different clusters of galaxies out there in the universe. So there we go. We can see these huge bubbles that were painted in blue. Really, we wouldn't be able to see them at all, that are being the source of matter that we just can't see. So we can try to map it, but we really don't know much about it. We can see its effects. It still doesn't tell us very much. And strangely, well, I'll get back to this point in a second. But let's first look at how astronomers are trying to detect it. In fact, there's been a few different attempts to try to find it, try to hunt down what it is. And so deep inside of a mine, the Sudan mine in Minnesota, a number of astronomers have put on their hard hats who trench down inside this mine and try to construct a lab that would help them detect if dark matter is a particle. So I think that maybe eventually dark matter will mess up and it might pluck something that is a normal piece of matter. Like it might actually go through something that's extremely dense and it might perturb it. So they created these large vats of very dense and very, very cold material. And they're hoping that a particle of dark matter will eventually strike it and cause them to take some information about that dark matter. But so far, nothing has gone through that they haven't been able to explain. And so even though this experiment has been going on for something like 15, 20 years, astronomers have not determined anything about dark matter. They haven't been able to prove if it's a particle. We still think it can be a particle. Some physics suggests that it could be that way, but we're not quite sure.
And just one little fun fact about the Sudan mine is actually the deepest mine in Minnesota and is one of very few mines that are actually get to be used for science. So it's pretty cool that we get to do that data, even if we don't learn too much.
Absolutely. So a little bit of a practical application of this is why should you care about dark matter? Because even though it's probably going through your body right now, you just don't interact with it. And the gravity affects the galaxies. The reason why dark matter matters is because we think that on the history of the universe, back after the Big Bang happened, the universe was so hot that in fact it wasn't able to clump up together normal matter. But since dark matter doesn't interact with that light and that energy, it was able to clump up, and it was able to give form to other galaxies and clumping up around it and stars. And so if it weren't for dark matter, we don't think that we would have normal stars and galaxies. We wouldn't be here today. That it helped the universe take form when everything else was so hot and energetic. So
basically, we wouldn't even be here without dark matter. We can't even see it, and yet it's so essential to life.
that's right. It's probably worth mentioning that dark matter makes up something like 25% of the universe. If we try to map out dark matter and we add up everything in the universe that we can see, all the energy and all the matter, that us, the atoms, make up only about 5% of normal matter in the universe, of matter in the universe. And then dark matter makes up like 25, 27%, makes up a lot more than there's the stuff that we're familiar with. So there's got to be a whole branch of physics left undiscovered for dark matter. And of course, then there's dark energy, which helps the universe expand. We'll answer more about that if you have questions in the question section. But let's transition into taking some of those questions. So if you have your questions, go ahead and populate them in the chat. We'll be reading them, and our chat moderator, Tara, will be keeping track of that.
Yeah, dark matter is a pretty crazy subject, so don't be afraid to ask questions. We'd love to answer them.
Now, Amanda's going to slowly zoom us through these dark matter clouds by asking your questions. But I want to remind everybody, while this is happening, that anybody can be a scientist. Even though it seems like Amanda and I are the ones telling you about the astronomy of the day, about dark matter, that every single one of you can be an astronomer. You just need to go outside and look at the stars. Try to make some patterns out of the stars. Look for planets. Maybe if you're lucky enough to have a telescope, you can use it to look at the moon, observe the different things in the night sky. There are other galaxies you can sometimes see. But not just being an astronomer, anybody can be a scientist. That whether you want to study geology, chemistry, biology, mathematics, engineering, any of those things are open to you if you're just willing to put in the hard work to learn it. And so I encourage you to try to study these things and learn about what interests you. I find dark matter particularly interesting. And that's why I really want to do this presentation for you today, because I think that dark matter is a big mystery in astronomy, and astronomers need to solve it at some point. So I hope that you can find a mystery that excites you. We have a question from Ricky. Hi, Ricky. I've read that some galaxies have more dark matter than others. Is that true? And what are theories about why some galaxies have more than others? That's a great question. We have noticed that some galaxies do not have almost any dark matter. It seems like they don't follow the rule that we've seen for almost all other galaxies. Now, I'm not terribly sure what some of the theories are, but even the discovery that some galaxies don't have dark matter or don't have this effect is new. So this is a fairly recent discovery. So I'm going to, I guess, ask Amanda, maybe ask our chat moderator Tara if they have any ideas on how to explain this. But while they are, yeah, Amanda, do you have a thought?
Not too terribly sure. Sorry about that. I honestly learned a lot about dark matter just getting ready for this show. It's a very, very interesting concept.
I think I could speculate and say it's probably the way that the universe formed, that even if dark matter began to pool in some places and allowed galaxies and stars to form around those, that there are probably some places that galaxies formed around without there having to be dark matter. There's just enough visible matter that it could just clump up by itself. And so even though dark matter might have laid the groundwork, there might be a few exceptions to that rule of where galaxies are. Just a thought. So maybe if they formed that way. So it's like almost all buildings are formed along the street or along a sidewalk, But some buildings are just put out in the middle of nowhere without there being a street or sidewalk. Let's see, a question from David. How did it get so hot to make dark matter? From Anna. So this is a great question. We think that the Big Bang levels of energy might have been essential to form dark matter. There are a few different theories. Actually, there are dozens of different theories about what dark matter could be and how it behaves. But some of them, most of them say that it probably had to form very early in the history of the universe. That you didn't just have visible matter form, but you had dark matter in tandem with visible matter forming.
Yeah, so the early universe was super hot.
We tried to bring up a graphic here, and it's a little bit warped because we're still expecting to be in the planetarium, but we are not in the planetarium, sadly.
There we go.
Here we go. So at the bottom shows way back in time, and the top represents the current day. So you can see the expansion of the universe throughout that time, and the very first nanoseconds of time changed a lot, of allowed the universe to take form, kind of set the ground rules at the beginning. Thank you, Ricky. Rick and Amanda, awesome. We are awesome. You're awesome. Why did dark matter get clumped together from David? From Eddie. Why did dark matter get clumped together? That's a great question. So strangely, astronomers think there are a few different types of matter, a few different types of dark matter, I should say. They think that it can be, maybe it can be hot, it can be warm, or it can be cold matter, dark matter. And so the sort of the hot dark matter would be kind of like very streamy, very tenuous, kind of like rivers, like tendrils, like tentacles coming out of these huge lobes of these big halos of dark matter. And cold dark matter would probably not move around too much. It'd probably have a much more stable, condition, I would say. That it's kind of like hot matter and cold matter, that we think that, strangely enough, dark matter can have more of like streams. It can go from being very streamy to very clumpy. And the clumps almost certainly came from it being very gravity intense. And we notice on large scales in the universe that galaxies and gravity tend to form things into sheets and strings and not necessarily just into clumps. So it's sort of a property of the way the universe formed and expanded going back very long time ago, 13.8 billion years, and then how it evolved from there. All right, is dark matter research done at CU? There are a few scientists who study and research dark matter. I think some of them have retired in the last decade or so. But there's a little bit of research done by dark matter, specifically, I'd say, by Dr. 𝐀𝐜𝐭𝐢𝐯𝐬. She is probably the foremost scientist I know on dark matter at CU. And I would say that others like Julie Comerford, John Bally, Andrew Hamilton, they study these very larger scale structures. It typically, the astronomers at CU study everything that is less related to cosmology. They have interest more in planets, about Mars and Jupiter and Pluto, as well as the size of galaxies and stars, the gas between the galaxies. Dr. Jim Green is certainly a big proponent of that. So I can't speak too much for dark matter research done at CU, but I know that a little bit is being done. And of course, Dr. Jack Burns does a little bit of research on, well, actually a lot of things, but especially the early history of our universe. So this is some great questions. And I want to propose everybody the social media challenge for this week. See, dark matter was essentially founded by Vera Rubin, that she carefully measured how fast spiral galaxies rotate. And so we're going to ask you if you can find something that spins or rotates, forms a spiral shape. Take a picture and tag us at hashtag dark matter, hashtag Fiske Planetarium, hashtag dome to home. We'd love to see your interaction with this. So next week we have coming up killer comets and asteroids. So that stuff is certainly going to be interesting. The death from the skies. It's not just all about black holes. You have to worry about things hitting the Earth all the time. So if you maybe want to go watch your favorite, maybe Armageddon or Deep Impact to get prepared for that, just being funny. Of course, our team will tune in next week. Anything else we should add, Amanda?
I don't believe so, other than thanks for coming, and hopefully you learned something. If your questions didn't get answered or you were too shy to ask a question, we will still answer them if you want to drop them in the chat or send us an email.
And if you want to help us fund these shows, then we would be very graciously receive any donations you might be willing to give. I know some people have been interested in donating to Fiske to help support this Dome to Home series. We'd be very grateful. But thank you very much for tuning in. I've been Nick. She was Amanda. Thank you for our chat moderator, Tara, and everybody on the back end, and for your questions. So we'll see you next week. We love you all, and have a great week.
Yeah, see you guys next time.